Hello, everyone. In this video, we're going to continue our work in section 4.4 and look at the two main theorems of this section. So let's first look at the total change theorem. So this theorem describes the relationship between the two expressions that we saw in the preliminary example. So let's just recall, in that example, we saw that the total change of meters from time A to B was equal to the integral of the velocity from A to B. And let's note that that velocity in relation to our position function is the rate of change of the position function. So what we could have said in the preliminary example is the following equality, that the integral from A to B of S prime of t, so the integral over the rate of change, is equal to the function evaluated at B minus the function evaluated at A. The total change theorem says exactly this statement in more generality. So let's fill it in together. So we have here the total change theorem. The integral of a rate of change gives the total change. So if we're talking about a rate of change of feet per second, then the integral gives us the total change of feet over that interval of seconds. So in other words, if f prime, so the derivative function or the rate of change function, is continuous, then the integral of the rate of change is equal to the change of the function at b minus a, or rather the change between f of a and b and f of b. So now let's look at that fundamental theorem of calculus. So if we reworded this total change theorem, we'd have the fundamental theorem of calculus. So rather than using a rate of change function in this theorem, we use the function whose derivative is f. So it's just a change of words here, change of vocabulary. So the fundamental theorem of calculus says if f is continuous and capital F is an antiderivative of little f, then the integral from a to b of f with respect to x is equal to the function f evaluated at b minus the function evaluated at a. And I just want to emphasize, what does it mean, antiderivative? So that means the following. So that means that f prime is equal to little f. So big F is an antiderivative of little f if the derivative of big F is equal to f. So it kind of goes the other way than the derivative. All right, so two comments that I just want to make here. These two theorems say the exact same thing, exactly the same thing. One is just using a rate of change function, and one is using the antiderivative. Number two here, the fundamental theorem of calculus gives us a way to calculate the exact value of an integral. So far, computing these integrals, we've had to use geometry by using kind of shapes under curves. We've had to approximate by chunking up the area under our curve into rectangles. But now we can actually get our hands on that value exactly. And how do we do that? Well, we can, provided that we can find an antiderivative of f, meaning we can find that function big F whose derivative is equal to little f. So we need to be able to find that antiderivative, because once we can find that antiderivative, then we evaluate it at b and a, find the difference. All right. Pretty amazing stuff. So it's okay if you need to take a moment to pause and meditate on this concept. If you are feeling like it, I also encourage you to take a little Google and Google tattoos of the fundamental theorem of calculus. You'll see that a lot of people have tattooed this amazing theorem on their bodies because it is so amazing. It tells us how we can compute total change by using areas and by evaluating our function. Pretty amazing. All right, and I'll meet you at the next video where we continue our work on section 4.4 and look at example 1.